Section 3.3 talks about interpreting and writing chemical equations and also balancing those equations. And I'm going to take just a little bit different an approach to this topic, particularly the balancing of the equations. And this is just going to require practice. That's all there is to it. But look at this first slide. It talks about in a chemical reaction, it's a chemical reaction simply describes a chemical change. Remember, Dalton said that chemical reactions happen when atoms are either joined together, pulled apart, or rearranged. That's what it's talking about in his third hypothesis of his theory. It's a rearranging of those atoms. She gives a couple of examples here, like the rusting of iron and the combination of hydrogen and oxygen to produce water. And we need to create some sort of way of explaining those things instead of just with words. And we do that with a chemical equation. But we have to do it correctly and we have to do it carefully. And I must say that this gives some students the most difficulty. You have to be so careful in how you do so because we have to use the correct symbols to do it. And that can get tricky. Here's one example right here. Ammonia. And ammonia, I do not want you to get mixed up with ammonium. Ammonium is the only positively charged polyatomic ion. It is an ion. Ammonia is a common name for nitrogen trihydride. That is the common name for that compound. So please don't get those two mixed up. So if you have ammonia and then you have hydrogen chloride, also known as hydrochloric acid, and I wish that she had said that, and they react together to produce ammonium chloride. Now, you're going to learn to take a word equation like ammonia and hydrochloric acid react to produce ammonium chloride, and you're going to write the symbols that go along with that. And in order to become proficient at doing that, which you're going to be required to do, the main number one, most important thing that you must remember, and I'm even going to write it, you must focus on writing the correct formula. You must focus. I've lost my pen, so I'm writing with my fingers, and you can sure tell it. You just have to write with the correct formulas, period. That's what trips most students up on this. And so that's what we're going to focus on for the rest of this lecture. All right. When you are writing chemical equations, you need to know what that this arrow that separates is called the yield sign. Excuse me, some of you that have taken high school chemistry already know, when you took it, that this is called the yield sign. And it separates the reactants on the left and the products on the right. And when we take this, we're going to recognize a few things. We always put the reactants on the left, and that's your starting substances, okay? And the products are what we end up with on the right-hand side. And so you've got to recognize a few things that we can't create or destroy. We can change and transform. That's what Dalton said. It's rearranging, but we cannot create or destroy. So we have to be sure that we write correct formulas. And we also want to be careful to, later on especially, to write symbols to represent, are we talking a solid, a liquid, or a gas? Because in the next few chapters, we're going to be talking about equilibrium and all kinds of things like that. So we're going to need to recognize what some symbols mean. For example, this little G in parentheses, it says that this ammonia is a gas at room temperature. Okay, this hydrochloric acid right here is also a gas at room temperature, and yet when they react together, they form a solid. That S there in parentheses means a solid. Okay, this L right here, oops, let me get that where you can see it better. This L means liquid, and then right here, this AQ in parentheses, that is aqueous, which means it is dissolved in water. It is an aqueous solution. It is a solution that has been dissolved in water. I will expect you to know these symbols and be able to use them appropriately when you're writing equations. A plus sign separates two reactants or two products. So if you have a plus sign in there, that means you have more than one reactant or more than one product. That's all it means. What if you have allotropes? Remember, allotropes are the exact same element, but they're in different forms like graphite and diamond. And if you have this situation, then you have to specify, okay, if we're talking carbon, are we talking graphite? Are we talking diamond? Or are we talking Buckminster fullerene? Which form of carbon are you talking about? Because they're both solids, so you have to then be more specific and show which one you're talking about. And then you can use helps when it comes to balancing, because that's another very important aspect of writing equations. And a lot of you should have your lab kits, and in your lab kits you're going to have a little molecular model set, and that is very, very helpful for some people that are visual. I'm a very visual person. I need to see it. And so if you'll take those little molecules out and you can actually put them in your hand and say, okay, if I have a diatomic molecule, and let's remember what diatomic means. It is so reactive. Remember the Brinkelhoff family I was telling you about? Those 7 elements that include hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine that will never be found alone. They will always pair up with another identical element. So you have that situation right here. You have hydrogen that is diatomic. And you have oxygen that is also diatomic. And these two react together to form water. But you remember what I told you in the very first slide of this section. You must focus on writing correct formulas. And when you write the correct formula for water, hydrogen, I'm not in pencil mode. You have hydrogen, it has a +1 charge. You have oxygen, it has a -2 charge. When you crisscross these, the correct formula is H2O. You have to write that as the correct formula. But what happened to this other oxygen? There's 2 oxygens here, and you have to have that O2 there, because that is the correct formula for oxygen. It will never just be O by itself, because it is diatomic. You must have this little 2 right here by that hydrogen, because it is also diatomic. So what in the world? Where did the other oxygen here go? See that little, there's only 1 oxygen right there. Where did the other one go? It is very, very tempting to just put another 2 down there. But now you've written an incorrect formula. And I'm going to say it again. You must focus on writing correct. You've got to write correct formulas. That has to be first. You have to write correct formulas for when they're by themselves, like this hydrogen and that oxygen. They're by themselves. If they're by themselves like that, uncombined, they have to have that little 2 down there because they're diatomic. But when they're combined, now you have to focus on what is their charge, what is their correct formula. Okay? And because of this, now, what did happen to that other oxygen? We cannot destroy matter. The law of conservation of mass says we cannot create or destroy. We can rearrange, but we cannot create or destroy. So in order for this reaction to occur, we would have to have 2 of these hydrogens. And then it's going to make 2 waters. Now we have 1, 2 oxygens, 1, 2 oxygens, 1, 2, 3, 4 hydrogens, 1, 2, 3, 4 hydrogens. Now everything is balanced and everything is okay in the universe because we did not destroy matter and we did not have a loose oxygen laying around out there. It is balanced. That is the whole purpose of balancing equations. And if you will use those molecules, if you're like me and you have to see it in action, those little molecules can help you to do that. And you can see, oh, I'm going to have a leftover oxygen. How can I keep that from happening? Well, if it had another hydrogen molecule to react with, you're going to end up with 2 water molecules being produced. It's like making cookies, a recipe of cookies. You have to have lots of different ingredients, but it makes a batch of 60 cookies, 5 dozen cookies. But it takes 2 eggs and it takes 2 cups of flour and different things like that if you're a baker. All right, in order to balance equations, I'm going to give you another way of doing so. I'm probably going to do a separate PowerPoint on just balancing equations, and I'm also going to put a little help slide out there as well, along with the videos that the higher and the lower ones I think I've already put on there for you. But in order to balance equations, this is what Dr. Berg has said. Burge, I've got to stop calling her Berg. Dr. Burge has said to, it does take practice. It takes a lot of practice. But in general, if you will do your compounds first, and also if you will, usually if you will save your hydrogens and oxygens for last, usually that's very helpful also. But if you'll do your compounds first, that's very helpful. And secondly, if you'll treat your polyatomics, you know your polyatomics, they act as gangs, they act as a single entity. So if they stay the same on both sides, and they most often do, treat them as if they are just a single element. That's very helpful also. And then make sure that everything stays balanced. Make sure to go back and double check to make sure that it's stayed balanced and that you have the same number of, say, oxygens and hydrogens on both sides. And we're going to, I'm going to save combustion because combustion reactions are by far and away the easiest when we get to predicting the products of reactions that we're going to do shortly. They are by far and away the easiest to predict the products to, because look here, every single combustion reaction ends in the same 2 things. It ends in carbon dioxide, CO2, and H2O. They always do. But the trade-off is they're the hardest to balance. They're very difficult to balance. So I'm going to give you some pointers for that. I think we need more practice with regular balancing before we tackle combustion. Combustion means burning. So it's burning something in the presence of oxygen. So every single combustion reaction, please notice this, every single combustion reaction, whether it says it in the problem or not, you cannot have a combustion reaction without adding oxygen. So it's usually going to be a hydrocarbon. When you go to the gas station, I went there last night, and it talks about octane. So if you put 87% octane, or if you splurge and get an 89 or a 91 or a 93, what that means is it's guaranteed to have that percentage be octane, and that means have 8 carbons in as its number of carbons rather. And then now it says 10% ethanol, that's C2. Well, I'm just going to draw it for you. It's C, and then it's got the H's here, and then it's got an OH. This OH makes an alcohol. So it's C2H125OH. That's its chemical formula. And so when you have alcohols and they burn also, they're going to get the exact same 2 products. They're going to get CO2 and H2O. And they're also always, combustion reactions will also generate heat every single time. But they're very difficult to balance. if they only have hydrogen and carbon right here, there's some tricks that I'm going to tell you later. But I want to wait, and I just want us to practice balancing other equations first before we get into these combustions. I want you to get a little bit more confident balancing other kinds of equations first. So here's one example that I want us to work on, and I'm going to show you how I would go about doing it. It may not be how Dr. Burge does it, but it's how I would go about doing so. As I've already told you, I'm extremely visual, and so I'm going to draw me a little line down so that I can separate out my reactants from my products. And I'll tell you why I draw a squiggly line, and that's for those of you that if you drew a straight line and it wasn't perfectly straight, you'd have to go find a ruler. Well, this negates that requirement, so that you have to go find a ruler and make it perfectly straight. Well, just make it squiggly and you don't have that to worry about. And then I'm going to circle every single thing. Here I have barium. Now here's hydroxide, and that's a polyatomic. So I'm going to look on the other side. Do I have hydroxide on the other side too? No, I do not. So I'm going to leave it as just being hydrogen and oxygen. So there's me some oxygen, okay? And then I also have some hydrogen there. And then the only other compound, or the other element rather, that I have is chlorine. So I'm going to write them right here. There's my barium, I have oxygen, I have hydrogen, and I have chlorine. That's what I have. And now I'm going to count how many of each of those do I have. And I'm going to have to really go back. I'm going to have to erase all that I did so that I can see my little colors, my subscript down there. There's my barium, there's my oxygen, there's my hydrogen, and there's my chlorine. I'm going to draw arrows. There's barium, oxygen, hydrogen, chlorine. Okay, I know that I have another oxygen right there and another hydrogen and oxygen right there, but I can add them in. How many total bariums do I have on my reactant side? I have 1. How many total? See this plus sign right here, plus sign right there. That means I'm going to add my reactants together, just like in algebra you were combining your like terms. Okay, I have 2. See that 2 gets distributed to the hydrogen and to the oxygen. I have 2 oxygen there, plus I have 4 there. So I have 2 there, plus I have 4 over here. So I have a total of 6 oxygens on this side. How many hydrogens? Well, I have 2 on here, plus I have 1 right there. So I have a total of 3. And then for my chlorines, I have 1. And then I'm going to write my elements in this same order on this other side. It's easier to keep up with them if you'll write them in the same order. And there's my chlorine. Please, I always write my chlorine, the L in chlorine, in cursive, so that I know that it's an L and not an I. So that's a good little hint for you as well. So I have how many bariums? 1. How many oxygens? Well, 2 times 4 is 8, plus 1 more over here is 9. For my hydrogens, I only have 2. And then for my chlorines, I have 2 times 1 is 2. Now, I have to make all of these things balance. For now, my bariums are balanced. I have this ClO4 over here. That is a polyatomic, and I have 2 of these ClO4s over here. What am I going to do about that? So I know I'm probably going to need a 2. I can't change a formula. Remember that. You cannot change a formula. So I know that I'm going to have to put a 2 in front of that. Please notice, though, that 2 is going to go distributed everywhere. That's going to change everything. It's going to change my chlorine, my hydrogen, and my oxygen. So now I'm going to have 2 of those chlorates, but how many hydrogens is that going to make me have? Well, I had 2 there. I had 1, 2, 3 there, but now I'm going to have 2, 4. Now I have 4. And what about my oxygens? I had 4 times 2 is 8. So now I have 10. So now what? Now my hydrogens are not balanced. I need a 2 in front of here as well. So now I have 2 times 2. That's going to fix this. That's going to be 10. 2 times 2 plus 8. And now I've got 4. Look at there. Everything's balanced. That's all I had to do, was put a 2 in front of my water and a 2 in front of that. I don't know if you can see that because it's kind of messy, but that's exactly what I did. Okay? And on another PowerPoint, I'm going to do combustion reactions separately for you because they are different. Now, she kept her chlorates together, which was smart, and I should have probably done that too. And that's exactly what she did. And she got Dr. Burge kept her chlorates together. Okay? And then this is a combustion reaction, and I'm going to do them separate for you. Okay? All right. Be expecting lots of homework on this.